Announcement number 4. If you signed up for 126 and are pre-med, this is proof that it will be important in your future life. Olivia took, I think she may have taken 101, 102, but the point is physics in the emergency room. It matters what kind of a battery you shove up your nose or other orifi. Okay. No, nothing? Okay. Orifi is plural of orifice, and, actually it isn't. Other orifices. Other announcements. I think that's pretty much it. Okay, I should probably not have social media up on the thing. God knows what could possibly go wrong. Right? Last time I had a string out and I was clotheslining you and all kinds of stuff, and I forgot I have lots of videos of this kind of stuff that would actually be better to look at. So last time we talked about things like this. We talked about waves on a string, right? So I have better views of it. When I was trying to let you see down the string, it looks something like this. You shake one end, and there goes the wave. Ooh, right? So if you shake something in time, you get a variation in space, right? That's what we talked about. Oh, who's that idiot here? And here's another one. This one's even better. Watch the pulse go. Here I want you to see that it doesn't just have to be a sinusoid. You can get any shape, in principle, can go down a string. It doesn't matter what the shape of the function is. Oh, that was fast. I'm sorry. Maybe there's a slow-mo. There's no slow-mo. It's fast. Okay. So we're going to look at a few examples like that because they're probably better than trying to watch them in real time. They're too fast in real time. Okay, so let's look at what we talked about mathematically here. All right, so we said the way we were describing that mathematically is we apply the laws of physics to a medium. If we apply the laws of physics to a psychic medium, it wouldn't take long. But here by medium, we just mean an extended system that has some property that we're going to interpret, or we're going to perturb, and we're going to watch it go, and we got a wave equation. And this was just for enrichment. We don't expect you to derive a wave equation. We don't expect you to solve a wave equation. I just wanted you to understand that like the equation that makes the oscillator, that describes the oscillator, there's an equation that describes all waves, and they all follow a very similar differential equation, just different physical systems put in different variables for the different medium, right? For the string, it's a deflection of the string. For air, it's the pressure of the gas, and all these things end up following basically the same wave equation. So we did, in a teeny bit of detail, the stretched string. The first wave, it's always your first wave, right? You got this thing, a wall, and a string, and maybe it's got some wave on it, like that. The wave could be going left or right, just like you saw here, right? The wave can go down a string. The book does sort of all this with different approaches and things called history graphs. So if you're someone who watches this and says, what the hell was that, and reads the book, understand the book approach is sort of way too detailed in my opinion. Okay, we don't need history graphs. This isn't interdisciplinary or whatever. And then there's a 3-page derivation on which way the wave goes. I'm going to show you that in a little less than 3 pages. And there's sort of a fake derivation of the wave equation in there. So the book gets really detailed. I'm just telling you what we need to know, okay? We can't turn this into my sophomore class. Okay, so the main thing to understand is you have a medium for now the stretched string. You have a wave equation, and there's multiple solutions to the wave equation and multiple types of solutions. So in this semester, in 125, all we care about is the traveling wave. Okay? Traveling wave. Next semester, we'll talk about standing waves. That's the other fundamental type, but right now it's just traveling wave. Okay? That's how I meet people. I just go around campus, hey. And where our solution to the traveling wave then was this. We called it D as a function of position and time, right? So D was like the deflection of the wave, up, and X was position, along, and time is just time. Okay? So we said, it's some A sine, and then we had these variables, Kx minus omega t plus phi. So we're going to play with those more today. And how to use them in problems and what they mean, but we did sort of define them last time. So this is a traveling wave because this describes a sinusoid moving in positive x. So by moving, we clearly mean it's a function of time. That's what moving means. Positive x direction. All right? And then we define these, and we'll talk about them more today, that k is a wave number. It's 2 pi over the wavelength. You might be more familiar with wavelength. And that omega, angular frequency, is 2 pi times the regular frequency in hertz. So this is like your high school things, F and lambda. Here's your college stuff, K and omega. I don't know. Graduate school, everything's imaginary and complex.